So good afternoon, everybody. I'm Anthea Fantina, and I thank you very much for inviting me here. It's my first time at CENTRA, and it looks very nice. I enjoyed my time here, even if it was short. So today I will speak about the neutron-star and the equation of state, and I will try to guide you through really introduction on neutron-star from the equation of state, and then I will give you some selected results in two astrophysical scenario. Mainly it will be called stars, but if I have some time at the end, I will address the problem of neutrons. So everybody of us knows, just to set the context in case someone neutrons are formed from supernova explosions, so we are looking at comparing to more than 8-10 solar masses that at the end of the night explode. We have here that's the neutron star or a black hole for more massive projector, but we stick to neutrons. And actually, the discovery of neutron star concept, which is rotating neutron star, was a bit fortuitous because this lady, just in the end of the 60s, she was looking at radio sources. And she realized that during her PhD, there is very long source. One knew potentially what it was. So some journalists call it little green money because they didn't know. But we know now that second friend is not in this name. So in the 17th actually was Jewish that got the Nobel Prize, but she's now very well recognized. So. And since then, we have there have been observed more than 3,000 pulsars, either isolated or in binaries. You see it actually here. When you see here plotting them with the period of rotation versus the period of and actually, through this kind of observation, one can do from the magnetic field, so it's not a direct observation, but thinking that if they slow down, it's because energy loss, and if we count it as magnetic field with a dipole shape, then one can guess the magnetic field. Then we can see that for some of the magnetic field is very high in Gauss, even more in the interior. So we do not just observe these properties, we observe others. I will come back to that. And if we go back to how they are formed, this is a quite complex scheme, but I would like you to retain a few points. So neutron stars are very hot, of course, because they are from the supernova explosion, which means that in the beginning the temperature is about 10 to the 10 or 11 Kelvin, or if you prefer, like us nuclear physicists, we speak about 11 MeV, so it's 1 to 10 MeV. And then after a few minutes, we have crust going to be formed. I will speak about the crust later. And then we do not mean that we create a cheese equilibrium. And then it starts to start emission, and then 10 to the 8 Kelvin stop. Maybe some of you can say, no, actually this is very object. But for us, nuclear physicists, this is cold because it means that the temperature is below the temperature. So this for us is to model this, we can think about they are at zero temperature. And this picture of full thermodynamic equilibrium called stars, then temperature is zero, with equilibrium, charge fraction are established at equilibrium, which means that the equation of state, so the relationship between the pressure and the density or the energy density, is just one dimensional. And then when they cool down, they have this such, or we call it in France a camembert. These are objects of 1 to 2 solar mass stars, the radio 10 kilometers, and the density, of course, varies, but you can reach a density that is higher, the density that you can find at the center of atomic, which is 3 minus 3, or you can put 2 times 10 to the 14. So this is again called the pitch. This video will show it during my talk. And as I said, some of these objects have very high magnetic field, but I will not. Now, picture of cold catalyzed crust, of course, is not always the case. The real picture is different from this picture. And these are some examples. For example, if you have accretion from a companion. These are binary systems where you have accretion of matter onto the neutron star. In this case, you can be out of equilibrium, so your equation of state not only depends on density but also on the charge fraction. Then you have proton neutrons. If you are cold enough, you have equilibrium of temperature. And now in the case of the more general cases where you have a hot neutron star, supernova, I know some of you work in supernova, or a post-merger in binary system, and then of course everything is out of equilibrium, so you have a weak interaction are out of equilibrium, and we have final temperature, we have the density, and so the equation of state in general because it depends on all these variables. So this is a much more problem. I will not address this talk. But even for cold stars, even if it's like a simplified picture, still is interesting for many astrophysical scenarios. One is, of course, when the neutron star is cold, so major isolated object, or for cooling, if you're cold enough, so to the 6th Kelvin, so it's relatively cold, you can use the nuclear physics, the zero temperature. Binary system in the spiral phase or up to merger, so pre-merger phase, zero temperature is okay. Even for glitches. Glitches, I don't know if you're familiar with that. Basically, the neutron star rotates, and then you have a variation of the time of rotation, and typically this decreases, but sometimes you have some sudden spins up, and you have glitches and ups. So in all this picture, this hypothesis holds. And even in that case, we are still really in extreme conditions because you see here in the temperature asymmetry diagram. Isoscene asymmetry means when the number of neutrons and protons is not the same. So you have a system. And you see here what we can problems or in accelerators. And then you see compatibility in general of neutrons. Again, when you have temperature, you see your difference is like a graph with it. Then you have core with homogeneous matter, but then you get hydrogen quarks, actually nobody thinks. So you immediately see that not all these conditions can be proven on Earth, so we have to resort to theoretical models. And then to consistently describe all this, it's very challenging. And I will try to convey what are the challenges. And another difficulty is that when we want to create solver, either from the nuclear physics point of view or from astrophysical point of view, unfortunately, it's never a direct connection because we have to go through 2 layers of modeling and through scales. So one layer of modeling is the nuclear physics part. Typically, you have nuclear theory, nuclear models that are calibrated in experiments with which you build your state, so the relationship of pressure, density, or impedance. And then you have to plug these into astrophysical model to be able to predict observation. And then one can hope to do previous engineering once one has observation, puts one thing on the underlying microphysics. So you see here that you go from observation, you have one side that goes from observation to modeling, and you go through several other of skills. So this is, of course, very, very challenging. Now, there is a case where this zero temperature case, when you can do connection between reaction state and observation in the quite primitive way. At least for what is static neutron star. And this is because we have generality. If you have a static object, then to build the structure of the neutron star, you only need to integrate an equation of hydrostatic equilibrium with some G, but still is hydrostatic equilibrium. And then if you want to model tidal deformability, this occurs when you have your equation state is spiraling, and then close enough, you have this tidal deformation, and then it's the same game. You have a differential equation, you integrate, start central pressure, central space, you integrate mass of the star, radius of the star, actually what connection with static station, which is a combination of the and so you see here structures. Actually, only when it's not already here because it is the relationship and the basic or the which means that in all this game you need the relationships. And then this is good because as I said, the correspondence is high. One to take for one time, so you have here two equations state, and for each student and the mass and the radius of state. Each equation state will plus. So what we define the neutron-star, each one with the mass and the radius. Then you change the equation state. You do the same with lambda, so the type of explanation, relation for equation states, but you have a relationship that are for static problem. And then you say, oh, but this is super, this is actually because this I measure the point here, I measure it in here, do the area, I trace it, I have my equation state, I have my composition. This is true in reality, in theory. In reality, this is not true because for start, observations can't travel back, so the point is also a rectangle. And then the main point is that the calculation of the equation state isn't a straight, and I will show you the uncertainties that are. And to do that, I will start from the text. So, you remember I have this section here that is the outer part. And because of the pressure that we have, because of the thermodynamic condition that we have started at the hydrostatic equilibrium, actually we arrange this temperature in loops, each of which is composed, at least in the outer part of the crystallized structure. Of course, the system becomes more dense as you go. And then you have in the denser part, the distance being here you have nuclei with electrons, and then at some point nuclei becomes so neutron that some of the neutron drift out, and so it's called neutron drift. And then you have the electrons nuclei within the system of electrons. And then we go back to the past. So the class actually only corresponds of 1%, but 1% of the mass is important to model many phenomena, glitches I mentioned before. And the idea is that to calculate the equation of state and composition of physics, 0 minimize the energy. So to principally it looks easy, then you minimize the energy. And so, which means that for each chance, you minimize the energy. If you imagine that at least density you have one representative nucleus, because this change with the density, one nucleus immersed in energy. The minimization of the energy gives the preferred nucleus for each layer and the immersed in the electrons. Now, for the class, which is the outermost layer, I said we minimize the energy. This reality is just the energy of the nucleus, right? Of course, you have some Coulomb interaction. And then the only way this inputs look like mass. So this job is relatively easy because masses are either experimentally observed, and my experimental colleagues do a great job. You have theoretical models that can predict the mass. And if you look at the composition, this is the number of protons in the nucleus, and this is the number of neutrons. So you see, you start from like this being iron nuclei, right? Because it comes from supernova, so it's makes sense. And the number of neutron increase means you have more than one. And now, if you want to know the details, these lines are built with particular model that is compressively model. Here, if you show but the main idea is that if we look where we separate part in the neutron chart, so this is the neutron number in the proton number. The neutron atoms, this is iron, this is nickel, then sewage, neutron rich, and then sewage. So my experimental colleagues, they can measure things that are known in this field. Very, very hard work. But when you arrive at the bottom of the task, you have theory to predict this kind of. Now, on the inside, we will do the story. We have nuclei, we have electrons, we have these three neutrons that are dripped out. And this is a challenge for the equation of state because you need a nuclear. You have to model nucleons in a dense medium. So this induces a choice of model and also a way to treat them. So do I treat them like a compressible liquid-run model? Do I treat it with full quantum approach? So this determines the main point. So it's a classical method like Thomas Fermi and so on. But the idea is always the same. You write a range, help you in. But since this is a bit more complex, it's actually you solve a system of equations and you have favorite composition. But since now you have the model, your equation of state is more uncertain than before, and I will show you. So now again the compositions, you see a similar to between 40 and 50%, it goes up here. But the number is in the nucleus goes up to 500, almost 1,000. These are very, very neutral. And then if we look at the equation of state, these are the prediction models. That in the other layers basically well established, right? Well established. And in the inner parts, you can still see some strength. And so it becomes a bit more model dependent. And then if we go at the inner parts, we have what we call neutron. So these are basically a non-spherical configuration because when you get very, very dense, your nucleus is not again spherical, but it tends to rearrange itself in either cylinder shapes, spaghetti for Italian colleagues here, or lasagne, or inverted configuration like cubes with whole sides, bucatini thing, or cubes. And so this is, of course, not directly observable, but is predicted by and you see here sequence and spheres. So when the cluster, you wouldn't call them nuclei, let's say clusters of nuclear spheres, and then you have the cylinder, and then slabs, so this is lasagna thing, and then so this actually occurs in a very, very thin layer, but since it's very dense, it actually can have some impact. Works that claim this can have some impact. For example, in pulsar evolution or oscillation or cold properties. So this is why people look at it. And I mean, it's possible to relate these more observable things to this, even if up to now it's predicted, but not so. Now, when we go to the core, it means we end the task and we go to very, very dense system. This is about half times saturation density. So nuclei do not exist. You have just neutron, protons, neutrons, of course they interact, muons, and then gluons. You have ions, quark, and neutrons. So you see, then you can also have additional particles. Of course, here the model dependence increases very much. And so if at the beginning I told you two equations say two mass radius relationship, in reality the picture is more possible. You have a paper in the equation of state with timeless that also makes me CENTRA equals relationship, relationship. So one move, of course, with observation to try to get out of the bad models, but still it's, I mean, the spread is large. And why is large, I told you, because on the one side you have nuclear and when you have very high density, you can have additional. So you can have the appearance of hyperons. This depends to the equation of state because you have the degrees of freedom to the system. So the pressure is distributed, goes down, and it can support less mass. Here, these are the hyperons, and these are only nucleons. And typically it gets a bit more compact, so it reduces the radii and also the ground stars. But the problem is, and this has been called in the literature of the hyperon puzzle, because when you put hyperons, the maximum mass decrease, and you cannot reach the two stars. In reality, it's more then that we do not have enough knowledge on this item, so it's varying with strength. And so the coupling constants are unknown, and so this leaves uncertainties. So they might be there, but we don't know. For the curve is less clear because depending on when the transition occurs and how, you can have models, okay, this is on nucleonic, and then sometimes you put the quark, say, quark value, and then you get things that are soft. Sometimes you get things that are stiffer, considering over maximum parts. So this is not clear, the amount of quarks. It depends on the model, how you do the transition, when the transition occurs. And then other difficulties that I was saying at the beginning when you try to do this reverse engineer is that what in the literature is called masquerading. Meaning that you can have different equation of state. As an example, the red one, there is two nucleons, and the green one is nucleus. So you can see here, put even measure something here to distinguish. So this is why it's called masquerade, because you can have cases where the same two different equation of state with two underlying hypotheses give you basically the same mass radius over this relationship. And so in view of these great uncertainties on the nuclear part, but also on the electron and quark, what is being often done in literature is to use the so-called agnostic model. Agnostic meaning non-nuclear. So these are typically models like polytropes, like speed of sound models, like Gaussian processes. So it's powerful because they do not assume any hypothesis on the composition or on the interaction. Just the model is to be causal, causality has to be stable, but nothing, I mean, very minimal hypothesis. You see the example here. Polytropes is with spectral representation or Gaussian is the blue. And this is defined in the condition by statistics. And actually, spectral representation was used to infer the constraints on the equation of state when GW17 was detected. But I would say the caveat, the problem with this model is that there's no information about nuclear physics. So if you want to apply them where you do need to know the compositions, like in cooling, this is not possible. And also, often these approaches use a unique equation of state for the crust. And I show you at the beginning that actually the crust has some uncertainty. So yeah, it depends what you do, of course, but there's this. And so this one way out, I mean, there are different, I will show you one, would say, way to do, and which is being developed in our group. And this is the so-called semi-agnostic approach. So I won't enter into the details, nor on the part, don't worry. There are papers out you can ask me. The idea is that you will have immunity, so only nucleons, sorry. No quark, no electrons, only nucleons, which in principle we should know. And you have a function, so the energy is function of the neutron and proton densities, minimal function, which depends, of course, on some model. For those of you that are familiar with stuff, for this particular model, the parameter are the nuclear impurity. These are like nuclear compressibility, saturation density, or symmetry. For those. And then, if you remember my scheme at the beginning, you have a nuclear model, you can predict something that you want nucleic matter, so you confront with samples. But on the other side, you can take your main body fast and liberal to build an equation state and finally. And then this is quite good because it's a flexible, if you choose a flexible function, what it means, different model parameters are able in for this function. Here, you are able to reproduce given nuclear models, given functional, either RMS, relativistic mean field, or you can also do the parameter very largely because the model is flexible enough, and so you can do statistical analysis. This means Bayesian. And then, of course, if you want, you can tackle this approach to the equation of state to account for the possibility of larger uncertainty. So, and then we do the reverse and can get constraints. Now, for the results we show you in the following, for the crust, you will see results with composite. We won't go into the details. There are these papers here, and again, you can ask me at the end if you want. So, yeah, the idea is we can not only use the existing model, we can use vary the parameter space and so do Bayesian analysis. So you start with the prior and then you incorporate all the constraints you can. And so typically it means constraints from nuclear physics, experiments or theory, and then as you go to advanced steps, you have astrophysics, like measure the masses of neutron-star and so on. And it's exactly what we do. So we start from a large parameter space prior, and we use constraints both from nuclear data, like measure masses of nuclei that you can measure in terrestrial laboratories, and the initial calculations. So these are typical chiral effective field theory calculations. And then you can get constraints, say up to 1, 2 saturation rates. And then finance, we incorporate constraint of size species that was plus is two signals, computational rate and enough. And these constraints are more high density. So just to show you some examples from the low density, we have constraints from nuclear physics. So these are calculation of ab initio calculations, so in principle microscopic calculation, pure neutron. And this you can see in the slides. This is homogeneous system, only neutrons. But see, this calculation are size up to, at least they agree, that one constraint up to say 1.5 saturation. And it can be used to constrain your more phenomenological approaches or even these when you span the parameters. And then of course you have experiments. Don't look too much to this. Those who know these are some that's for proximity energy, whatever. But you have constraints from area ion collision, so collision collapse. You have polarizability. This means when the response of a nucleus to electromagnetic field. Then you have to measure the masses, response. So if you combine all of that, you see you don't have a perfect superposition. This is that you not the so you can get an idea of your parameter space to prove. Or what you can also do is to use emulators. So you can collect all the knowledge that you can have from experiments, like again, measure masses or charge radii of nuclei, and then use a manual method to try to constrain this model parameter. In any case, if you have an idea of how to constrain your equation of state at low density. And at high density, you have physics and some numerical consequences is correction done with those, and some of them then sizely, given delays at about size, really less precise, but still this is the results from nicer that is mounted on the axis. You have found that the probability to now we have only one, say, measurement prediction that is the challenge 17 can be with any event. And we can, of course, plug this probability function into our Bayesian system. What's come out of that? What come out of that is that if you start with a large time, like we should say, and then you start plugging into your constraints, you see that if you plug constraints to nuclear physics, you reduce densities, intensities. If you put astrophysics, means masses, computational waves, you use lots of density, and then you combine everything and you actually fine. It looks thin, but it looks thin, so we still haven't seen it. See, you can get a relatively narrow. Now, this is corresponding to the mass relationship we want to pursue. So you can see here once again the effect of all the constants. Then you can now basically the only hypothesis here in what I'm showing is the nucleonic composition. I'm assuming that there are no additional particles. So you can say, but this measurement is this is compatible with the observation, which does not mean that it's a proof that there are no additional. What it means is that up to now, observations are not constraining enough to say it exists or it doesn't. These are it's just that observations are not constrained. Now, this is again the same thing as this from here, just in a different column, and compared with actually some popular nuclear movement statistics. So you can see that some of them are very compatible with the constraints in the gravitational wave or gas. One has to be careful when applying nuclear models of physics, but with some even with posterior constraints. And this is actually when mass radius in another complementary approach, and you set things. So as soon as you assume only two points, these are which, as I said, compatible with observation, meaning observation has to be more precise to pinpoint the position. Now, at the beginning, I told you that it's very challenging to give a consistent description of all the properties of the. And I would like to spend 2 or 3 slides on this point because actually the fact that having consistent, thermodynamically consistent and so-called unified equation of state is important. Why? Because having non-unified equation of state, it means that you have different models for the different region of the stars. So what you do, you glue, match equation of state for each piece ones, class ones, the core, and so on. So this, of course, some people do that because calculating the equation of state for the class is harder. But this will induce times. So you see here this mass and this relationship, and the difference among these curves is just the fact that different equation of states have been glued. So it's completely spurious. And so you can have about, let's say, 500 meters, almost a kilometer, which would be the precision of what could be claimed for some future measurements. In reality, we are using physics. And the same for the. So this is why from the physics community, there has been an effort to produce thermodynamically consistent and unified equation of state. Not many are available. That is not there are stored, but there are not many available at the moment. But there is an effort from the community in this aspect. And I would like to show another example with this Bayesian framework of having a non-unified approach. So class and core that are not consistent. This is an example for the class-core transition. So this is this point here, class and the core. For example, for modeling glitches, if you remember. And this consists here the priors, the launch, and this is when you put all these postulates. Look at physics, you still answer, used uncertainty, still answer. Of course, if you use only one class, one model for the class, you have one model for the class gives you 1 point, while density and pressure for the class of and so which means that if you want to do Bayesian inference, the use of unique class completely erases your answer. So this is one of the reasons why we have devised a tool that is actually, so if you want to check it out, that is able to reconstruct a consistent equation of state starting from a high density equation of state. You have your high density equation of state, we are able to reconstruct in a consistent way the crust, and so the full equation of state would be unified. Currently available is version 1, but version 2 should come out next. And another fact is the second transition, in effect of the radius and tidal deformability. The figure is very touched, I know that's green. So this is the prediction of the radius 1.4 mass this. The reason one is the prediction consistent model. And then if you put only one model per class, you have the data show. If you change your equation of state, which means that it's the same thing here. Actually, this is very long. So time probability. You see here that when there's a fixed path, it merge to the extra. About few percent difference, even though this is the position claimed by future generation telescopes, so this can be important for the future, but okay, it's not much. And the detector is okay. Well, the system begins under the scene. And then you see this orange here, the effect of constraints from traditional wave references. So the idea is that if you have a non-consistent approach, especially if you don't constrain to combination calculation, actually the uncertainties are understanding consistent approach. So I think it's worth to actually take it into account. Now you might be a bit depressed, so okay, she told us that these are very uncertain, we cannot learn much from the movement, so this for the future. And so we have to discriminate. Of course, there's nuclear physics, which I won't speak about because I will more focus here on astrophysics, which might be more of interest for you. But of course, we have nuclear physics. There are experiments on the way which can constrain, of course, at low density. And from the astrophysical point of view, well, one possibility is having more precise data. Now we have a distribution for this one. Imagine that tomorrow we get a precise measurement, right? And you constrain because you see the lines that constrain and it looks good. Another possibility is the same looking at observation. What this means? It means that this is the probability. This is this prediction with this Napoleonic models by from the beginning, just before. In this line of constraints from the population. Now things are computer. Imagine a maximum mass of a neutron-star to solar mass. If tomorrow they tell me, no, we observe a neutron-star, we observe the neutron-star with 2.5, then my nucleonic hypothesis would be my prediction, which would be issue with this measurement. Which means that if this was the case, it would be an indication of the possibility of actual. So this actually nucleonic hypothesis, which seems a bit reduction, is actually can be used as a null hypothesis. So if I observe something that does not agree, then it's an indication for example. Another possibility is to have a switch. So this is simulated tie down to the function of the number of observation with Nash. So you can see here that with faithful estimation, you can recover the engine the equation set. So this could help us in pinning down equation set. Or consistent detector. This is again simulated signal this is bias. So this is the ratio between the probability of having a phase transition with respect to the one not having phase transition. So if you see that this is high, it means that you can have it. And you can detect it. Because these are related as a function of the distance of binary E. So you can see that, I mean, each time we end up is far with the precision of third generation galaxy. This is the exposure of H. So if the transition of Q. So you have transition from normal to quark method to saturation density. So relatively. Otherwise, it's up to disentangle in these mergers. And then another possibility is to do post-merger. So if we are able to measure after merger, this could be done with future generations. Then I show here some examples. We don't have hope to be able to track this transition. And this is an example. This is the frequency of the post-merger signal is a function of this side to the form. When you see that emission no emission impact, and here we have some with the core. So as you can see here, I mean, these two models are strong phase transitions. This is not, the smooth is really strong. So once again, I mean, you can detect transitions for the studies. But otherwise, things can be mixed up. I mean, it would be hard to disentangle from other factors, like, you know, modified gravity or whatever. So it would be hard. That's all. That's all. Now, if I have another 5 minutes, I will briefly go to the second point, which is proto-neutron-star cluster, so finite temperature. And why this is interesting? Because if you remember my point at the beginning, I told you that neutrons are hot, and then they cool down. And at some point we start in beta equilibrium, but still okay. So if this is the case, for proto-neutron star, this is the picture I was telling you at the beginning, like in a crystalline structure. But then the picture is not anymore. This would be rather Venus mononuclear because statistical physics tell us that if I am at the temperature, I have several microstars. So I have several. And these are actually calculations, function of temperature. Let's look at one of these, time that I'm having. This is the prediction of the speed line for this picture. And this dotted line is the average in this loop extent. This can be quick. So, this means that if I perform my energy minimization, if I cross, I don't have any more one nucleus, I have a distribution. So, the minimization gives me a distribution. The K and Z of all these. Now at some point the crust will crystallize, so it will become soft, and then typically the composition freezes because reactions when the composition to change, right? It depends also on the cooling time space. This has to be evaluated. As a matter of fact, if this is the case, if even the composition is frozen at some finite temperature or above, it means that in reality the proto-neutron star composition can be different in the catalyzed picture I showed you in the talk. And the second, so you see the function of one component, and you see in the corner different that's the actual distribution of it. And this means that there are impurities, so what in literature are called impurities. Impurities means simply the variance charge, the variance. And actually, this impurity factor in astrophysics, typically in full simulation, is taken as free parameter that is adjusted to reproduce observation. And this is an example of the period derivative. And you see the lines are all the simulations with my collaborators. And in this course, you see that the impurity parameter is 0.1 constant until some point where it's changed by the I found and these notes are stations. So from these, it seems that to reproduce these some data, you need to be performance. And so, but this usually is not tuned, this value is tuned to the observation. What we have done, I don't go into detail, but is to calculate in a self-consistent way. So we've calculated the distribution of the and you see here in the direction of the catalyzed one component, and you see in violet the actual distribution in Z, so number of protons and number of protons plus neutrons. And you see here that you can even have polymodal distribution with the very light movement. So this means that we expect the impurity factor to change, because if this is the variance, this is the division. And here it should be proven. And this is indeed news. This is a calculation for the outer crust, and this is the inner crust. So you see here that you can have, for example, motion terms, it's not constant at all. These are the externalization terms. And we can go up, well, I don't know, so this is probably. And yeah, these are this actually it's this clear. What we can see here is that this model the model they use, what we can see is typical since that the contribution of variance of Z come essentially from the nuclear distribution depths or to the presence of plastic phase as claimed by simple. Why this is because, as I said, there is consequences for a plastic. This is a competition in the past. Some the factor of time exchange rate. There is consequences, for example, in cooling, in ranking of some system. This is a mathematical system actually with different because of the participation. So typically what it means is that this is typically cooling curve or even like curves of a Cretan system. So we just conclude here. I hope I convinced you that nuclear physics plus astrophysics can give constraints in the equation of state. Sometimes it's hard to discriminate, but there's a potential for future, pin down or discovery. For now, nucleonic hypothesis is still compatible. So we need, of course, more precise or numerous astrophysical observation, possibly post-merger, to see if there is indeed a phase transition. And of course, we need a reliable theoretical model to be able to make more reliable prediction and interpretation of astrophysical observation. Then I show you, some tool, the performance of a tool that we devised to construct consistent equation of state and the importance of a multi-component calculation. I leave here some open questions that we think are still there. So when we use constraints, often is not raw data. So the model dependence of constraints and that one can infer, both from nuclear and physics actually. And then the uncertain equation of state might have different effects. And so this is also something one has to take care. And of course, to microphysics input, like the equation of state in history modeling, I think one has to really consistently implement this microscopic input, perform systematic of Bayesian studies to assess the real uncertainty. And then, of course, one has to, I spoke only about static properties, but dynamical are of importance, especially for some of the and I will stop here. I thank you very much for your attention.
Hannes, you had a question.
Yes. So just one or two slides back about the conductivity.
Yeah.
So it's varying quite a lot.
Yeah.
So how can I understand this?
Yes. Is that the scope the composition zero temperature, yes, assuming no impurity. Okay, and so they do this like this really solid lines. Now, this is something that no, this is fixed temperature. Okay. They saw some variation. One explanation for that, actually, is that when you have your composition that varies typically because of shell structure, like shell effects, you can have a variation of the composition quite, and you have the consequence is that you can have some jump in the one component, and in the multi-component you have smoother things, but still, if you have structure effect, you can have a higher variation of the impurity factor, means that your crust is an alternation of a pure, say, conductive layer or resistive layers. And this is why you can have this variation of the impurity parameter layers. And this, when you plug into the transport coefficient, has this effect, at least in this study. But the idea is that, yes, as soon as you have impurities, of course, you change your scattering and your transport, and therefore your transport coefficient change. And so one can expect that cooling changes, which is, but this is like of accretion system, but it's different in pure. It's not the only uncertainty. I just show this part same time. The shall we is another story.
More questions?
How much does these studies then impact on space?
I didn't have the time to go into like higher energy part, but of course there are experimental experiments that are say researched or planned to go more to the higher. And this could give us information on things like interaction with additional particles or reforms or quarks or even hadron coupling. This could help in constraining the coupling constant of
Because the principle strangeness is special.
Yeah. Indeed, in the results that you've seen before, there was no additional, so it's only nucleus. So these no, for the results I showed you, I don't know. This is what I was saying here. The only assumption here is that this nuclear composition. So this is why I was saying about this new lattices, because it's very much my prediction only relies on the assumption that is one, which is found with large ones. Then it's an indication of a conditional content, exotic content. So for now, from these results, there's still no addition, no more, no particles. But indeed, from the nuclear physics point of view, there are experiments that are meant to provide dense energy, and this in principle should give us some indication on the properties of these guys. So this constrains our operation state. Or there are models in which I show an example over here, or in here, where it is transition to we don't specify to something else. Again, this is this summary. And then we've seen that with some astrophysical observation like gravitational wave, you can have the detection of strong indication of the presence of result if the transition occurs strongly or if it's a This is what comes out from this diagram and many studies. But for now it's indication, and then we'll go with the more constrained observation to try to pin down.
Any more questions?
So you also talked about
The results.
so that it's like one thing that we need to know how to elaborate more on that on because that's important to know that people don't really can but how we would switch and say higher depth.
No. Well, we can talk later. I have other slides, but just as a quick answer. So the meta model is used for, of course, for the homogeneous part. Then you need a mini body for the crust, which myself is a flexible neutron model. So you have to add this parameter for the cluster. So this is taken into account. Now for the high density, for the results I showed the Bayesian analysis, we still keep the meta modeling also with displays for nuclear. So we do prediction assuming only nucleus, and then now, of course, your observation about high density, this is it. You can go into causality problem and so on. We are very well aware of that. This is why some people in our group also worked in the relativistic meta model kind, and we saw that the prediction, this is prediction, and this is nuclei, and this is compatible with what we find with. Now they are also working on the microns, I don't think the paper is okay, but some colleagues in the group do work on that. And then the other possibility, some of the plots I showed after, is to match this meta model to a more class. This is also possible. This is what we now actually we had matched it with, well, in this case, a simple polytropic, just to take into account of a higher variability. But you can, in principle, with this idea of even a high density equation of state, construct a crust, because we know at least until saturation density we should not have a transition principle. So it's nuclear exception. And then this is why when we include minimum at saturation. And then with this principle you can plug the equation of state, the general one, you reconstruct the unified way. We have the nuclear this is with all things.
Could you show the ones to where it is very much?
Or this one or whatever.
So we have two branches, right?
No.
Increase the mass. As you increase the mass, you increase the rate, right?
Yeah, well, again, these are results of pure nucleonic stuff, so the two branches are not there because there's no transition in this kind of plot. If you think about the two branches like a nucleonic and a non-nucleonic one, this is not the case here.
No, I'm saying that on the equation of state, the
Yes.
solution gives two branches.
No. No. The equation of state here, one is the one you showed. If you don't assume phase transition, you have one equation of state and you have one family. One family means that is the family of neutron-star. Yeah, okay. This is a different, okay, sorry, because when I think about two branch, I think about this one. You have one nucleonic branch and non-nucleonic branch. So, no single value. This one up, try to go to the one you were talking about. Yeah, in some cases you can. Yes, in some cases, yeah. You have some cases managed to
When I think it's a stable state.
Well, the stability in principle is given when you have a decreasing plus with respect to this. And this, I think, is not the case here. In the pure it occurs here because then your dm over d rho or yeah is such that you go unstable and then you would go in a this is why this stop and have maximums. Otherwise you would have the one which is the unstable.
So I have one final question about the glitches that you spoke about a little bit. So if I understand correctly, this happens in rotating neutron stars where the crust does not rotate with the same speed as the fluid, let's say, inside, right?
Yeah,
It somehow
yeah.
resonate.
Yeah, I'm not an expert on this. This one I don't see my collaborator is working on that. Let's say that the reason for glitches there are different. So there has been at some point the idea that there was like storm quakes, so these quakes in the crust. On the other, but yeah, it's true that I would say common accepted one is the idea of superfluidity. So indeed, if you have a superfluid, you don't rotate at the same speed and you have formation of vortices. And then when the difference between the rotational velocities too much, then you have this spinning, and so the angular momentum is transferred to
Okay.
and then there are also actually anti-glitches that we observe. So
Okay. One last question.
So I would like to ask about thermodynamic consistency. talk about. So when you talk about thermodynamic consistency here, you mean basically that
Of thermodynamically preserved, and the laws of thermodynamics are preserved, and there's the relation, the thermodynamic relation hold. So you don't have, because you can have for some equation of state that if you have some inconsistency or some non-monotonicity due to numerica, sometimes,
I think what is cheap, for example, monotonic and
unless you have a first transition, then. But in principle, as it should, because this is pressure is established by the equilibrium, so it's something that is there by.
exactly. So and then, so you talked about this Qt code. So I would like to understand what you then do for this low density
Yeah.
as that you thermodynamically.
I went quickly because I mean this requires some, but we can discuss, of course. So what we do is that typically at high density you have an equation of state, so a relationship. We speak T equals rho, a relation between the energy and the density. And typical, if your equation of state comes from some nuclear module, you have some nuclear properties. So if you have that, we have a way. There is a way. It has been shown that it is possible to actually how can I say, reconstruct and rebuild the full set of parameters. So if you start with some isoscalar one, we are able to reconstruct the isovector one, so symmetry, energy, and so on. And then, but basically the idea is start from epsilon of n, so energy versus density, and beta equilibrium, and there is a way to actually connect this with the nuclear parameter, extract the nuclear parameter that we can use as an input parameter in the functional, and with the very same functional build it. So this is a bit the idea. I can go into equation with you, there's no problem. But the idea is really that one. You start from a high density energy versus density relation, beta equilibrium. If you have some nuclear parameters, it's better because we need them for the crust, and then we can reconstruct the isovector and the energy versus density in all the region. And then we apply compressive overloaded model for the crust for sake of time. And then you have the full equation of state and composition of the crust.
Okay.
But we can discuss, you can come and I show you the equation.
Okay, I guess we can stop here with the questions, but we can find her. Let's thank Anthea again.
If you enjoyed the video, like and subscribe.